Ever wondered how medieval people built ships that sailed oceans for decades without power tools? Master shipwrights used only hand tools and natural materials. Their methods often outperformed modern techniques in durability. Traditional joinery distributed stress better than welding. Clinker hull construction. Medieval shipbuilders perfected clinker construction, where overlapping wooden planks created hulls more flexible and durable than modern welded steel. Each plank overlapped the one below, creating a stepped appearance that distributed stress across the entire hull structure. This technique allowed ships to flex with waves rather than fighting them, preventing hull cracks that plague rigid modern construction. Clinker hulls were lighter yet stronger than solid timber construction, requiring fewer materials while providing superior seaworthiness. The overlapping design created natural drainage channels and self-reinforcing structures that lasted centuries. Iron fastening systems. Medieval blacksmiths created iron fastenings that lasted centuries without corrosion through hand-forging techniques that produced superior metal grain structure compared to modern mass-produced fasteners. Each rivet, bolt, and clamp was individually heated and hammered, creating dense, corrosion-resistant iron with crystalline structures that modern industrial processes cannot replicate. Different iron compositions were selected for specific applications: soft iron for flexibility, hard iron for strength, and wrought iron for maximum corrosion resistance. The hand-forging process eliminated air pockets and impurities that weaken modern fasteners. These custom-made fastenings were sized precisely for each application, distributing loads effectively throughout ship structures while maintaining integrity for decades longer than modern hardware. Natural wood selection. Medieval ship developed sophisticated wood selection and seasoning processes that produced timber stronger and more durable than modern pressure-treated lumber. Tree selection involved harvesting specific species during optimal seasons when sap content was lowest, ensuring maximum density and minimal shrinkage during construction. Seasoning techniques included controlled drying periods lasting 2 to 7 years. That removed moisture while preserving wood strength and flexibility. Different wood types served specific functions: oak for strength, pine for flexibility, cedar for rot resistance. Natural seasoning processes created wood with superior grain structure and resin distribution that provided inherent waterproofing and pest resistance. Storage methods protected seasoning timber from weather damage while allowing controlled air circulation. Quality assessment involved testing wood density, checking for defects, and verifying moisture content using traditional methods. Properly seasoned medieval timber remained structurally sound for centuries while maintaining workability with hand tools, rope, and fiber rigging. Networks. Medieval rope makers created rigging systems using natural fibers that provided superior flexibility and strength compared to modern synthetic rigging, while offering easier field repair and replacement capabilities. Hemp, flax, and other plant fibers were processed through traditional methods that preserved fiber strength while creating rope with optimal stretch characteristics for sailing applications. Rope construction techniques included specific twisting patterns that distributed load evenly while preventing unraveling under stress. Different rope weights and constructions served specialized functions: light cordage for sail handling, heavy hawsers for anchoring, and specialized lines for specific rigging applications. Natural fiber ropes provided superior grip characteristics that prevented slipping during manual handling operations. Rope preservation techniques using tar and natural oils protected fibers from saltwater damage while maintaining flexibility. Splicing and repair methods allowed field maintenance using simple tools and materials available aboard ship. These natural rigging systems required regular maintenance but could be completely rebuilt. Using shipboard resources during extended voyages, tar and pitch waterproofing. Medieval shipbuilders developed comprehensive waterproofing systems using pine, tar, and natural pitch that created more effective seals than modern synthetic caulking, while providing self-healing properties that extended hull life significantly. Tar production involved slow-cooking pine wood in covered pits that extracted resinous compounds with superior waterproofing and preservative characteristics. Pitch preparation combined tar with other organic materials that enhanced adhesion and flexibility, while maintaining waterproof integrity through temperature variations. Application techniques included heating tar mixtures to optimal consistency, for deep penetration into wood grain and joint spaces. Caulking methods used oakum fiber soaked in tar that was driven into seams using specialized tools, creating expandable seals that tightened with moisture exposure. Maintenance procedures included regular tar application that could be performed during voyages using shipboard heating methods. Different tar formulations served specific applications: thin coats for surface protection, thick applications for major sealing, and specialized mixtures for underwater hull areas. These natural waterproofing systems actually improved over time as tar compounds penetrated deeper into wood while providing renewable protection that could be refreshed indefinitely using available materials. Sail weaving and canvas production. Medieval textile workers created sail canvas that surpassed modern synthetic sails in durability, repairability, and wind handling characteristics through traditional weaving techniques and natural fiber processing methods. Linen production involved growing, harvesting, and processing flax plants using methods that preserved maximum fiber strength while creating uniform threads suitable for heavy-duty weaving applications. Weaving techniques used specialized looms that produced canvas with precise thread counts and tension distributions optimized for sail applications, requiring strength, flexibility, and wind resistance. Different weave patterns created varying sail characteristics: tight weaves for storm sails, loose weaves for light wind applications, and reinforced patterns for high-stress areas. Canvas treatment involved natural processes that enhanced water resistance while maintaining breathability that prevented mold and rot during storage, edge finishing, and attachment systems that distributed wind loads effectively throughout sail structure. Repair procedures used patching, darning, and reweaving techniques that could be performed aboard ship using carried materials and tools. Operational during extended voyages when replacement materials were unavailable through modern supply networks. Wood shaping techniques. Medieval shipwrights developed hand tool techniques that shaped timber with precision exceeding modern power tool capabilities while preserving wood grain structure and natural strength characteristics that machine processing precip often destroys. Adds work involved controlled chopping motions that removed material while following natural wood grain patterns, creating shaped timbers with superior strength-to-weight ratios compared to machine-cut lumber. Plane techniques included specialized tools for different shaping applications: smoothing planes for finishing, molding planes for decorative work, and compass planes for curved surfaces. Draw knife methods enabled precise material removal while maintaining complete control over cutting depth and grain orientation throughout shaping processes. Chisel work created precise joints and detailed shaping that fitted components together with tolerances matching. Modern machine capabilities. Steam bending techniques used controlled heat and moisture that allowed wood shaping without structural damage, while creating curved components impossible to achieve through cutting methods. Template systems ensured consistent component shapes throughout construction while accommodating natural wood variations. Tool maintenance included sharpening, handle replacement, and blade adjustment techniques that maintained optimal cutting performance throughout construction projects. These manual shaping methods produced components with superior grain, orientation, and structural integrity while enabling customization and adjustment that machine processing cannot provide during actual construction activities. Traditional joinery. Medieval shipbuilders created joint systems that held ships together using interlocking wood connections that distributed stress more effectively than modern fastener-dependent construction while providing superior flexibility and longevity. Dovetailed joints provided permanent connections that could not be pulled apart while distributing forces across maximum wood surface area for superior strength characteristics. Scarf joints joined timber end-to-end using overlapping cuts that created connections stronger than solid wood while enabling construction of components longer than available timber lengths. Wedge systems provided adjustable tension that could be modified during construction or maintenance while maintaining tight joint tolerances throughout service life. Traditional wood glues, made from animal products and plant resins, created bonds that penetrated wood grain while remaining flexible, enough to accommodate wood movement without failure. Joint cutting techniques required precise hand tool work that created perfect fits without gaps while maintaining wood grain integrity throughout connection areas. Assembly procedures included systematic joint fitting that ensured proper load, distribution while accommodating wood shrinkage and expansion throughout service life. These traditional joinery methods created ship structures that remained tight and strong for decades, while enabling repair and reconstruction using available materials and traditional woodworking skills, rather than requiring specialized industrial equipment or synthetic materials. Natural navigation. Medieval craftsmen manufactured navigation instruments using traditional methods and natural materials that provided accuracy matching modern electronic equipment while offering complete independence from external systems and power sources. Compass construction involved magnetizing iron needles using lodestone while creating balanced pivot systems that ensured accurate directional indication despite ship movement and magnetic interference. Astrolabe production required precise methods that created graduated scales and sighting systems capable of accurate celestial navigation using sun and star positions. Quadrant construction involved mathematical calculations and careful craftsmanship that enabled altitude measurements essential for determining latitude position during ocean voyages. Sundial creation included gnomon positioning and hour marking that provided accurate timekeeping necessary for navigation calculations and daily ship operations. Chart making involved careful measurement and artistic skills that recorded coastlines, hazards, and navigation information on durable materials using permanent inks and protective treatments. Plumb line systems provided depth measurement capabilities that enabled safe navigation in coastal waters while identifying underwater hazards and anchorage conditions. Weather glass construction created barometric pressure indicators that predicted weather changes crucial for sailing decisions and storm avoidance. Lead line production involved weight casting and line marking that enabled accurate depth measurement, and bottom sampling for navigation and anchoring applications. These traditional navigation tools required no external power sources while providing complete navigation capability that enabled successful ocean voyages, lasting months or years, without reliance on modern electronic systems that can fail during extended operations. Ballast and weight distribution. Medieval ship designers developed ballast systems that optimized vessel stability and performance. Through careful weight distribution using natural materials and mathematical principles that surpassed modern computer-calculated ballasting methods. Stone ballast selection involved choosing rocks with appropriate density and shape, characteristics that provided maximum stability while minimizing cargo. Space loss. Lead ballast casting created custom-shaped weights that fitted hull contours perfectly while providing concentrated mass in optimal locations for stability enhancement. Sand ballast systems offered adjustable weight distribution that could be modified during voyages based on cargo loading and sailing conditions. Ballast positioning followed mathematical principles that optimized center of gravity location while maintaining proper trim characteristics for different sailing conditions. Weight calculation methods determined optimal ballast quantities that ensured adequate stability while preserving cargo capacity throughout various loading conditions. These traditional ballasting methods created vessels with superior stability characteristics that enabled safe ocean voyaging for different cargo requirements throughout vessel service life. Mast and spar construction. Medieval shipbuilders created mast and spar systems that provided superior strength and flexibility compared to modern aluminum rigging while offering complete repairability using shipboard resources and traditional woodworking techniques. Tree selection involved identifying specific species and individual trees that possessed appropriate grain structure, taper, and dimensions for different rigging applications. Timber preparation included controlled seasoning processes that preserved wood strength while eliminating defects that could cause failure under sailing loads. Shaping techniques used traditional tools and methods that preserved wood grain integrity while creating optimal aerodynamic profiles throughout spar length. Joining methods enabled construction of spars longer than available timber through scarf joints and reinforcement techniques that created connections stronger than solid wood. Reinforcement systems included iron bands and rope wrapping that strengthened high-stress areas while maintaining spar flexibility, essential for proper sail performance. Maintenance procedures included inspection, repair, and protective treatments that could be performed during voyages using carried supplies and traditional techniques. These traditional mast systems provided superior performance characteristics while offering complete maintainability that kept vessels operational during extended oceanic voyages. Hull repair and maintenance. Medieval shipwrights developed comprehensive hull maintenance systems that enabled complete vessel repair and reconstruction using shipboard resources and traditional techniques that surpassed modern repair capabilities in versatility and effectiveness. Damage assessment involved traditional inspection methods that identified structural problems, wear patterns, and potential failure points while determining appropriate repair. Strategies using available materials and techniques. Plank replacement. Procedures enabled complete hull reconstruction using carried timber, traditional tools, and shipboard woodworking capabilities that could address major damage during extended voyages. Caulking renewal systems included complete seam renovation using oakum, tar, and traditional techniques that restored hull integrity while improving upon original waterproofing performance. Structural reinforcement methods involved sister framing, doubling, and internal strengthening techniques that restored or enhanced hull strength using available timber and traditional joinery methods. Underwater repair techniques enabled hull maintenance below waterline using diving methods, temporary patching, and specialized tools that addressed damage without requiring dry dock facilities. Preventive maintenance included systematic inspection schedules, protective treatments, and component replacement programs that prevented major failures while extending vessel service life significantly. Tool maintenance ensured shipboard repair capabilities through systematic care, sharpening and replacement of specialized woodworking and metalworking tools essential for vessel maintenance. Material storage systems maintained adequate supplies of timber, metal, rope, tar, and other materials necessary for comprehensive repair capabilities during extended voyages. Emergency procedures addressed catastrophic damage through temporary repairs, jury rigging, and survival techniques that enabled vessel survival and crew safety during extreme situations. Documentation methods recorded maintenance history, repair procedures, and vessel modifications that guided future maintenance decisions and preserved institutional knowledge throughout vessel service life. These traditional maintenance systems enabled medieval vessels to remain operational for decades, while maintaining seaworthiness and performance standards that exceeded many modern vessels. Dependent on shore-based industrial support facilities and specialized synthetic materials, unavailable during oceanic operations. These medieval shipbuilding techniques prove that traditional craftsmanship achieved remarkable maritime engineering without modern tools or synthetic materials. Their methods often produced superior results through natural material properties, traditional joinery, and construction techniques that improved with age rather than deteriorating like modern systems. Ready to discover more ancient engineering secrets that outperform modern technology. Subscribe for weekly craftsmanship wisdom that could revolutionize your building projects today.